Okay, so welcome everyone to this virtual talk, and I hope you're all doing well. So I'm going to talk about some sketching load ones for maximal matchings and MIS problem, and this is joint work with Gillat and Rotem Oshman. So a quick definition of the problems. In maximal matching problem, the goal is to find a matching, namely a vertex disjoint collection of edges, such that it's also maximal, meaning that there is no way to extend it. This is not a proper subset of any other match. Similarly, in the MIS problem, the goal is to find an independent set, namely a set of vertices which are not adjacent to each other, which is also maximal. Namely, it's not a proper subset of any other independent set. And we're going to study this problem in the sketching model. Here we have our input graph, and there is a processor on every vertex of this graph. And each processor is going to see the edges of that vertex. Basically, it means that vertices have unique ID, and each processor is going to get to see a list of IDs corresponding to the ID of neighboring vertices. Important thing here to notice is that an edge is going to be seen by two different processors. Now, in addition to these processors, we also have a referee, sometimes called a central coordinator. And the way it works is that all the processors are going to look at their input and simultaneously with each other will send a message to this referee. And we're going to call each of these messages a sketch because it's basically a summary of the neighborhood of each vertex. Now the referee is going to look at these sketches and output a solution to some problem over this graph. And one thing to note here is that we're going to assume that there is a shared source of randomness given to both referee and the players. This is called a public randomness, meaning that the players have access to the same source of randomness. Now, this model is sometimes also called broadcast congested clique model, and when we are focusing on one-run algorithms. And also it's closely related to dynamic graph streaming. So the question we want to understand is how to find a matching or MIS in this graph. So let's say if this is a maximal matching of this graph, we require the referee to be able to output such a collection of edges. Now on the surface, there's nothing interesting happening here. Every problem can be solved trivially with order and size messages, by just each node sending all the edges that it possesses to the referee. But this is too much communication. And in this model, we are interested in minimizing the communication between the players and the referee. And in particular, we are really interested in getting a communication efficient protocol with polylogarithmic size sketches in the size of the graph. So the question we want to understand is that, is there any communication efficient protocol for either of these problems? Now, before I talk about our result, let me first tell you a bit more about this model, because on the surface, it may look like there's nothing you can do in this model. In fact, let's just look at a very basic problem. Can we find a spanning tree of such a graph? This is a collection of two cliques connected by this edge. And this edge is definitely necessary for any spanning tree in this graph. At the same time, if I look at any endpoint of this edge, what's going to happen is that this edge is going to look identical to any other edge on this processor. So how is it possible that one of these endpoints is able to communicate this edge to the referee? And now this is where the interesting things in this model happen, is that the processors are sharing edges. So some vertex here, by talking about this edge, can indirectly inform the referee about this edge as well. So to make this concrete, let me show you a concrete solution to this problem. Let's look at the IDs of vertices, and this partitioning, suppose it's known to the referee, but not to the players. So what we are going to do is to give a number to every edge. Let's say we are going to give 2 times the number of vertices plus 1 to this one, 21, 65 here, 43. This is basically the largest ID times the number of vertices plus a smaller ID. This way we'll get a unique name for each edge. Now, every vertex is going to look at the edges incident on itself and going to treat them as follows. If the other endpoint is larger, it's going to write the minus that number over the edge. So this is 54. 5 is larger, it's going to write -5, 54. If it's a smaller, it's going to write 41, 42, and 43. So with this convention, what's going to happen is that each node is just going to sum up the numbers they have and send that to the referee. So this node is going to compute -51, 43, 31, and 21, this number, and send it. Same way here, and note that now it's going to add 21 instead of subtracting, because 2 now possesses this edge. We do the same thing this way, and let's ignore this part of the graph, it doesn't even matter. Each vertex is just sending order log n bit messages this way. And what is going to happen is that the referee is going to receive all these messages. It's going to add up all these messages for the vertices here. And suddenly we are going to get the idea of this edge map. So the referee is able to find what was this edge. There's nothing too magical happening here. I mean, we added and subtracted the same number over every edge except for this edge. So we were able to find this one. But the important takeaway is that in this model, vertices can directly inform the referee about the edges of other vertices even. And that's very important for us. Now I showed you some concrete solution to some rather artificial problem, but this is basically the basis of this super nice result by An, Gohan, McGregor that gives a log n to the power 3 size sketches for finding a spanning forest of any graph. It's a randomized algorithm that works with high probability. And here and throughout the talk, n is going to be number of vertices. And in fact, starting from this breakthrough result, there have been numerous results in this model that gives algorithms for lots of different problems. And I want to in particular highlight this recent result from last year that that gives an algorithm even for the delta plus 1 vertex coloring, again with log cube and size messages. The reason I'm highlighting this is that this is a problem very closely related to maximal matching and maximal independence. Based on this result, one might wonder whether such result or such sketches are also possible for these problems. So now with that background, let me tell you what is our result. Our main result is that unlike these other problems, neither maximal matching nor maximal independence set admit an efficient sketch. In fact, any sketch that we have for either of these problems requires essentially a square root n sized communication from an average player, or at least from at least one player. Good. And just to give you some context is that previously we knew some omega n lower bound for linear sketches. These are a certain type of sketches that corresponds to taking linear transformation of the neighborhood of each vertex. They are not as general as an arbitrary sketch. And such lower bounds follow from graph streaming lower bounds. But for general sketches, we did not have any lower bound other than some trivial omega log n. Good. Now, one thing I want to point right away is that our result proved that there is no efficient sketch for this problem, meaning that we need more than polylog n, at least a square root n. But it's not actually clear whether a square root n is the right answer to this problem. Maybe one can get even an omega n lower bound, or maybe the correct answer is order square root n. However, one thing we know is that square root n is not very far-fetched also. In fact, if we only had one extra round of sketching, then there is a protocol with order square root n communication for both of the problems. Good. Okay, so that's our result. And for the rest of the talk, I'm going to tell you a bit more about our lower bound for maximal matching, then show how it will also employ lower bound for MIS, and then conclude the talk. So the lower bound for maximal matching is going to be a communication complexity lower bound with multiple players. In fact, more formally, we prove a theorem like this, that there exists some distribution on n-vertex graph such that any protocol for maximal matching on graph sample from this distribution that has a relatively small error, let's say 1 over 100, needs almost a square root and a communication. And here I stated it from at least one vertex. And we're going to see shortly where does this term come from. So one thing I should point out here is that what do I mean by error? There are two notions of error. One is that the protocol is allowed to output something which is a non-maximal matching. In that case, it errs. But it may also output a non-edge in the matching. Basically, output a pair of vertices which there is no edge in the input graph. This is interestingly, not many of the previous lower bounds in the literature allow for such type of error. So they assume that the algorithm always output a matching, but it might not be maximal. And in fact, the only other work that I know on related problems such as maximal matching is this very nice result by Dark and Conrad from CCC 2020. One other thing I should point out here is that here I stated the lower bound that we need this much communication from at least one vertex. In the paper, we show that in fact this can be improved from communication on almost all the vertices. On average, vertices need to communicate this much. Okay. So now let me talk about how do we prove this theorem. And the proof, a starting point is to use this very remarkable family of graph called RS graph or Ruzsa-Szemeredi graphs. So quick definition, a matching in a graph is called induced if between this set of vertices there is no other edges. So this is an induced matching because between the red vertices there are no other edges other than the match. And this is not an induced matching because of these two other edges. And now a graph is called an RT-RS graph if it has T edge disjoint induced matchings of size R. So this graph on the right is a 3-4 RS graph. This is one induced matching, another one, another one. In general, we are interested in finding RS graphs where both R and T are large parameters with respect to the size of the graph. These are counterintuitive construction because an induced matching is a locally sparse graph, but we want our graph to be locally sparse, full of induced matchings, but at the same time globally dense, have many, many matchings and so many edges. Good. And in fact, we are going to use the following construction by Ruzsa-Szemeredi that gives matchings of size almost linear and like an asymptotically linear number of such matchings. And now you'll see why did we have that 2 to the log, the square root log n term in our bounds. So the hard distribution of graphs we talked about, it looked like a graph like this. So what is this? It's basically a correction of n RS graphs, each of them on capital N vertices. Let's be a bit more precise. Think of picking capital N RS graphs. Here, these are 2x4 RS graphs. And then from each of them, pick one induced matching uniformly at random. And after you did that, merge all the other vertices to become one. Okay, so these green vertices, they are the same across all RS graphs. And if you look, these green vertices and blue vertices form one RS graph, green and orange form another, and so on. And that's our graph really, modulo just some redrawing. So I'm going to call these green vertices public. They participate in many RS graphs. And the other vertices private. Each color corresponds to exactly one of these RS graphs. And it's easy to see that I'm going to have n public vertices and roughly n square private vertices. Another thing which is easy to see in this graph is that for large enough capital N, any maximal matching has to pick many, many edges from between private vertices, many of such edges. The reason is simply because there are too few public vertices, and so we have to pick these edges. To be a bit more concrete, we have capital N public vertices and n square private vertices. So no matter how we match public to private, there are many, many edges that the maximal matching has to pick from here. That's the algorithm task. It has to reveal many, many private edges to the referee. And that's the task we are going to prove it's hard. A bit more concretely, it means that the mutual information between the message of the players and the set of private edges has to be omega n square, proportional to the number of private edges, private edges. Okay, so let me tell you a bit how we prove such a thing. We are going to treat public and private vertices differently. Public vertices are very hard to work with. The reason is that they have a complete knowledge of which induced matching in the RS graph is important. They know these red edges. And because of this edge sharing phenomenon that we have, they can in fact talk about these red edges directly to the referee. That makes life hard, but the good thing is that the way we can handle them is that there are not too many public vertices. So what we are going to do is to simply bound the information they reveal about the private edges by the total size of the messages they send. Okay, so this is a trivial bond, essentially. This is more, what happens for the private vertices is more interesting. These vertices do not know which one is the special induced matching. And the reason is that from their perspective, all other vertices look the same. So it might as well be that these two is the important edge. In this case, because they do not know which edges incident on them are important, they have to reveal information about all induced matchings so that they can reveal information about the special one. And so the way we can handle these private vertices is that we are going to prove that one bit of communication from a private vertex only reveals roughly 1 bit of information about these private edges. And that's basically in terms of the mutual information. The information they reveal is 1/n smaller than the size of the messages they have. This is some, you need to do some work to prove this thing. This is based on a direct sum argument using information theoretic tools, but we have to be slightly careful to prove this result. So it's not a straightforward corollary of direct sum results. Good. So what happens is that public vertices can reveal information proportional to their messages, and private vertices will reveal information 1/n factor smaller than their total messages. So let's put all these things together. We have n public vertex, n square private vertex, and they have to together reveal omega n square information about these edges. But if the bandwidth of each of them is smaller than n, the public vertices can only reveal order n square, the total message size, a small of n square. And the private vertices can reveal n cubed divided by n because of that discount factor. Again, a small of n square. And so life is good. What happened is that in general, in total, they could only reveal a small of n square bits about private edges, as opposed to the omega n square we wanted. That's the lower one, basically. Now notice that this graph has n square vertices with a capital N square vertices, and when we reparameterize, we got a lower bound of a square root n, essentially. And that's the proof for maximal match. Okay, so now let me also tell you briefly how do we prove the lower bound for MIS. One thing that comes into mind is that, well, MIS on the line graph corresponds to maximal matching of the original graph. So why don't we do just this standard reduction? The problem is that if you do such a reduction, you're going from the original graph to the line graph, which requires you to put a processor on every edge of the graph. And this is not possible. This will create a lot of overhead in the messages and break the lower bound. So instead, we are going to give a reduction between the problems, but it only works for the particular hard instances that we have and the type of lower bound we prove. Let me show you briefly how does the reduction work. We are going to take two identical copies of the graphs from the maximal matching. We are going to connect all the public vertices between them to each other. So that's the graph. And so the claim we have is that any MIS in this graph, no matter what type of an MIS we find, is going to reveal many edges between private vertices. The reason is the following. Suppose one public vertex on one side of this graph belongs to the MIS, let's say this vertex. Now we're going to just ignore this part. The interesting thing is that in the other part of the graph, none of the public vertices can be in the MIS. It means that all of their edges are out. And so we are only left with these private edges and the matching between them. And so any MIS has to pick one vertex from endpoint of each of these edges. And what we can show is that this is enough information for our lower bound to kick in. Okay. So showing, even revealing one vertex as the endpoint of each of private edges is going to, or lower bound is going to show that even this is too much information revealed from the private edges, and we are able to prove the lower bound. And basically, that's how we get the result for maximal independence. Okay, so now let me wrap up quickly. What we prove is an omega square root n size lower bound for sketches of maximal matching and MIS problem. The main idea in our proof was to partition the vertices into a small number of informative vertices, the public vertices, and a large number of low information vertices, private vertices, and then bond the information revealed about each of them based on their messages differently, and then get the final lower bound. Now, as for open problems, there are a couple of nice open problems after our work. The obvious one is that can we get tight bonds for either of these problems in the model? The current upper bound is order n, the lower bound is omega square root n. Can we close this gap? An approach for making the lower bound stronger is to look at these highly informative vertices and try to bond the information revealed by them a bit more accurately. And in fact, the one good idea to try is to consider a hierarchy of vertices based on the information they reveal. For instance, we have on one end, we have public vertices. Then we have vertices that every bit that they send reveals half a bit of information about this special edges. Then the vertices which every bit they send reveals 1/4, and so on and so forth, up until the private vertices that every bit they send reveals only 1/n. And if we can create a construction with such a hierarchy of different vertices, we might be able to get an omega and lower. Another very interesting problem here is to try to prove better multi-round algorithms or lower bounds for this problem. Here, multi-round means that in each round, the player sends a message to the referee. Referee is going to reveal the messages of everyone, and then you're going to continue. And in such a model, we know an order log n round algorithm for matching and log n for MIS. I should mention that the second algorithm works only on average log n communication per vertex in each round. Okay, so this is not worst case, but average. And finally, I showed you a reduction between matching and MIS in this model, but it only worked in a very special setting for our hard instances. Is there a general reduction between the two problems in this model? I think that would be very interesting. And at the very least, will also give us a log n round algorithm for the matching. Okay, that's all I wanted to say. And let me know or send me an email if you have any question about this stuff. Thank you for listening to the talk.